Hello. This is the last quiz, finally. Yeah, let me go over the quiz 12 about regression. Actually, this quiz is much easier than the previous chapters because linear regression is just combination of everything we learned earlier. So, given all the practices you have done, it's just the results. So, it's pretty straightforward. Okay, let me start. A fan of television game shows has observed that, in general, the more educated the contestant, the less money he or she wins. To test her belief, she gathers data about the last 5 winners of her favorite game show. She records their winnings in dollars and the number of years of education. The data are as follows. Right, data, 5 observations, right, like that. She estimated a regression model using winnings as the dependent variable y and the years of education as the independent variable x. So she used the ordinary least squares estimator. What is the predicted change in winnings when the education of the winner increases by a year? Okay, so your education predicts the winnings in a game show, right? So to handle that, this is the regression model we have in mind. Y is the winnings, beta, like X is the years of education. So beta 1 is the effect of education on your winnings, right? Or you may interpret it like this. The change in winnings when you are educated one more year, right? And beta 0 is intercept, which is the expected winning if your education is 0. So this doesn't mean a lot in the context because there is no one who has 0 education. So anyhow, and in here we would like to know what is the predicted change in winnings when the education of the winner increases by year. Exactly, that is beta 1, right? So when education increases by year, how much y increases, that is beta 1. So you may use 2 different ways. So first of all, it is always more convenient to use Excel, of course. So I will copy the numbers. 12, 16, 12, 16, 14. And 700, 400, 600, 400, 400. So from here, I suggest 2 different ways. First, you may just use regression tool built in Excel, or you may use the formula by calculating covariance and variance separately. Okay, so let me try the regression method. So, here, click on data sheet. You choose data analysis and regression in the menu. And then Y is winnings, 5 observations, and X is education. And then just click, right? Then you get the results. And of course, the results are calculated based on the ordinary least squares. So what you need is, this is what you wanted, minus 62.5. So it's interesting, when your education increases, your winning decreases, right? So that is based on the data, because as you see, the highest winner is 12 years of education, which is the lowest education, and the second highest winner is also the lowest educated people, right? So because of that, in the data, it looks like a negative effect. That is true in this data. Of course, the data are fake, I made up. And the second method is using covariance. Covariance between this and this divided by variance of x, which is education, right? Because x is multiplied, you have to divide them, then you will get the same number. Okay, so this is the same same method you can use. In the end, you are going to get the same method. by the way, when you calculate the covariance and variance, one thing you have to be careful is I match the formula. Here, I use sample covariance and sample variance formula. But if you use population covariance, then you need to use population variance too, right? As long as you match the formula, your result must be the same. So either way, you can calculate beta 1. Okay, that is question number 1. Question number 2. Suppose that a random sample of 220-year-old man is selected and that their height and weight are recorded. A regression of weight on height yields an intercept estimate of -90 and a slope estimate of 4.5, where weight is measured in pounds, height in inches. What is the regression's weight prediction for a man who is 60 inches tall? Okay, so it's simple. Our setup is like this. Y is weight. So I assume that weight is determined by your height, right? And then beta 1 can be interpreted as when you become taller, if you are taller by 1 inch, and then how much you'd weigh more, right? That is beta 1, right? And beta, in the question, beta 0 is estimated to be -90, and beta 1 is 4.5. So if you are 1 inch taller, then your weight will increase by 4.5 pounds, right? And what's interesting here is, so -90, how can y be minus? It's weight. -90 pounds are not possible in physics, right? But anyhow, it doesn't mean anything because this is weight if your height is 0. Of course, no one can have 0 height, so it doesn't mean anything. Just a mathematical number. So then we would like to predict when x is 60. When x is 60, then just plug in. So assuming epsilon is 0, error is 0, plug in 60 into x, and beta 0, beta 1's estimates into their places. So we have -90 for beta 0 plus 4.5, which is beta 1, times 60 for x. So then you calculate that. That is the predicted weight. Okay, pretty straightforward. Next one. The superintendent of a school district must decide whether to hire additional teachers. If she hires the teachers, the student-teacher ratio will drop by 2, and student performance will improve, right? Of course, more teachers will improve students' performance. Under the assumption that student performance is measured by a test score, she estimated a regression model using the test score as the dependent variable and the student-teacher ratio as the independent variable. The intercept and the coefficient are estimated to be 650 and -5 respectively. If she hires additional teachers to reduce the ratio by 2, what would be its predicted effect on the test score, right? So if you hire additional teachers, the student-teacher ratio will drop by 2. Then what would happen to the test score? Again, the linear regression model again. Y is test score or student performance measure, and X is student-teacher ratio, right? If X increases, that means, so by the way, the student-teacher ratio means how many students a teacher has to handle, right? So the smaller the better, the smaller the better. So when student-teacher ratio increases, that means a teacher has to handle more students. So we expect the test score, student performance will drop. So in that case, of course, beta 1 will be negative because the beta 1 is the effect of student-teacher ratio on performance. So if the greater x, the worse, then of course beta 1 will be negative, and that's our estimate, right? And then, so beta 1 measures what happens if x increases by 1. But I'm assuming that x will decrease by 2. So increase by 1 results in drop by 5. But when x decreases by 2, then you can easily say that y will increase by 10, right? So 1 increase will make 5 drop by 5, then it goes the other way, and then double, right? So that is coming from the linear model assumption. So everything is linear. So if you double, then the effect will be doubled, right? And if you multiply -1, change the opposite direction, then everything will just be multiplied by -1. So pretty simple algebra. Next one. A farmer wants to conduct a regression analysis to study the relationship between the bushels of corn per acre, y, and the amount of fertilizer used per acre, x. So consider the corn produced as the dependent variable and the amount of fertilizer as the independent variable. Suppose that the sample mean and standard deviation of y are like that, and sample mean for x like that. Furthermore, their covariance is 12. Find the predicted amount of corn produced per acre when 20 pounds of fertilizer is used per acre, right? So we are going to use OLS model and estimate the OLS estimate using those informations, right? Covariances. So again, the model goes like this. Y is corn yield, and x is fertilizer. How much? The more fertilizer you use, then of course I expect you're going to get better yield, right? So beta 1 is that effect. If you use 1 more pound per acre fertilizer, then you are going to increase the corn produced per acre by beta 1 bushels. So that is beta 1. So then how can we calculate them? Remember, this is the formula. Beta 1, OLS beta 1, OLS estimator is calculated as the ratio between covariance and variance, which are given. Covariance is 12. Variance of x is the standard deviation of x squared. So standard deviation of x is 2, so its variance must be 4, 2 squared. So as a result, covariance is 3. And then the intercept, beta 0, requires sample means. Y's sample average is 63, x is 18, and beta 1 is used here again. So if you calculate them, you get -9, right? So then as a result, your prediction, if you like to predict the yield when you use 20 pounds of fertilizer, then it goes like that. So, right, so beta 0 is estimated to be -9, beta 1 is estimated to be 3, and x is assumed to be 20. So calculate what you get. That is your prediction. Okay, so straightforward. Next, the capital asset pricing model, CAPM model, it's really famous model, is the most fundamental model for modern finance. It calculates the relationship between the market return and the return from an individual risky financial asset. So we set the linear regression type model where y is the financial assets return, annual return, and x is the annual market return. Beta 0 can be interpreted as the risk-free return, and beta 1 is the effect from the market condition, right? So given the market situation, we are interested in the performance of a stock or company, right? The residual epsilon is the excess return over the market condition. So even if you know the market condition, there may be some shocks to each individual firm. So sometimes an individual firm may outperform the expectation or worse than the expectation. So that's the excessive return. Suppose that, by the way, in typical CAPM model, beta 0 is called alpha and beta 1 is called beta. So, but in our notation, we call them beta 0 and beta 1. But typically, in finance, they just say what is alpha, what is beta, right? But if you are familiar with finance, then maybe you must have heard about that. And suppose that beta 0 and beta 1 are estimated to be 2 and 1.2 respectively. In a year, the market return was 5%, but the asset return was 11%. What is the estimated excess return for the asset in the year? So I write so the question is long, but in the end, what I'm doing here is to calculate the residual. The residual, it is what we are calculating. So again, the linear regression model is set like this. Y is the return from an asset, and X is the market return. So we assume asset return can be explained by the market situation, and beta 1 is the systematic risk. So when market goes up, the economic cycle is like this. So of course the firm's performance follows the cycle. So that is the beta 1. How much it follows the market cycle is captured by beta 1. And then you can first you have to calculate the expected return. So we know beta 0 is estimated to be 2, beta 1, 1.2. And we assume in a year, so we saw that the market return was 5%. So then you expect the firm, the asset, to increase by 8% in that year. That is systematic return following the cycle, the market cycle. However, actual realization was 11%. So that means that firm, that asset, outperformed the expected return. So the minus 3 plus 3% point is the residual, which is exactly the excess return we defined in the question. Okay, so pretty simple algebra. Next, suppose that an equity analyst at a prestigious investment bank wants to determine the relationship between a corporation's sales and the price of the corporation's stock. So sales and stock for a firm. She assumes that the stock prices are the dependent variable in this relationship, while sales are the independent variable. So from the monthly observations for the past 5 years, the following results are obtained. So we assume that the stock price can be explained by the firm's sales. So we do the regression and we obtained a point estimator, and its standard errors. So this is the relationship. So that means when sales increases by $1, the stock price, $1 million, by the way, say, sales is measured in $1 million, then the stock price will increase by $4.44. That's the meaning of this. And this coefficient intercept means when sales is 0, stock price will be $13.45. Of course, means nothing. And here, given these results, estimation results, consider the following one-tailed hypothesis testing. So you believe that this effect, the effect of sales, must be at most $3, right? 3 or lower. You believe it is 3. It will not. You don't believe. You think it cannot be greater than $3. So your alternative is greater than 3. Upper tail test, right? So you are rejecting only if beta 1 is greater than 3. So here find the p-value, right? So then our setup, again, same linear regression model. Stock price is y, x is sales, and beta 1 is the effect of sales on stock price. Clear. In this model, we have hypotheses like this. Beta 1, we believe beta 1 is 3, but our estimation is 4.44. So the t-statistic is the standardized difference between your estimate and your belief. So your estimate minus your belief standardized by the standard errors. So that is 1.6. And then given this t-statistic, we would like to calculate the p-value. But remember, it is an upper tail test. You reject only on the upside, right? So your p-value must be calculated only on the right tail. So given 1.6, you are calculating that. So let's try that. So cumulative probability is norm.s.dist 1.6 true. So the cumulative probability is probability smaller than 1.6. But what we want is greater than 1.6. That is this number, right? So the answer is 5.48%. So the p-value is 5.48%, and the null hypothesis is rejected at 10% because p-value is smaller than the significance level 10%. Okay, that's how you make the decision. Next question. Now we handle multiple variables. To study the per capita consumption of chicken in the United States, you are given the data on the following variables. Interesting question. Chicken consumption per capita. Y is per capita consumption of chicken in pounds. So we'd like to explain why. And to explain why, we include disposable income, your income, and the chicken price, as well as pork price and beef price, right? So from microeconomic theory, it is known that the demand for a commodity generally depends on the income and the price of that commodity and the prices of substitute or complementary commodities, right? So it's like you learned like income effect, substitution effect, in the demand theory chapter, I believe. So in view of these considerations, a multiple regression model is estimated, and the following table shows the results. Oh, before looking at the data, let's think about this. So when income increases, I expect the chicken consumption will increase. You are going to have more chicken, right? So I expect the coefficient of x1 will be positive. And if chicken price increases, of course chicken consumption will decrease. That is the demand theory, demand function. So it will be minus. But now what's interesting is pork and beef. So when pork becomes too expensive, more expensive, then those who used to consume pork will now substitute pork for chicken, right? I think so. So like if pork price increase, if pork is getting expensive, then people will reduce pork consumption. Instead, they are going to choose chicken as an alternative, right? Some of them will turn to chicken instead of pork. So the coefficient of x3 will be positive. In a similar manner, I believe x4 will be positive. So let's see. What is interesting is this is negative, right? As income increases, the chicken consumption decreases, then from the microeconomic standpoint, the income effect is minus. So maybe chicken is inferior good. So if you are richer, then you may consume more steak than chicken, maybe. I don't know. But anyhow, the data are fake. It's a fake data. So what we need is we need to find all statistically significant variables at the significance level of 5%. So 5% significance level is what we are looking for. So the idea goes like this. So remember, statistical significance is based on the hypothesis testing of 0. So if a coefficient is 0, and if that null hypothesis, again, if the null hypothesis that a coefficient equals 0 is rejected, then we say the coefficient is statistically significant, right? So you don't like a coefficient to be 0, then the variable is irrelevant in your regression model, so that is the worst. So you want to reject it. You'd like to reject it, and you want to say this is statistically significant. Then basically we would like to do this hypothesis testing. So the t-statistic, first we need to calculate the t-statistic. So beta hat is the estimate, and I denote the null hypothesis H0 beta. Beta given in the H0 is your belief. So estimate minus your belief standardized by the standard deviation of your estimate. But as I said, we are interested in hypothesis about 0. So this part, beta 0, beta H0 is 0. So simply your t-statistic is the ratio between your point estimates and standard errors. So that is how you calculate the t-statistic. So I calculate t-statistic like that. Just ratios. The ratios are simple. And then, based on these, you may calculate the p-values by yourself. That is possible, but I would use the t-statistic approach to simplify the decision. We know that at 5%, by the way, this is two-tailed test. So at 5%, you are going to reject the null hypothesis if the t-statistic is outside of plus minus 1.96. You remember that. So plus minus 1.96 is the threshold. So given that, you need to find. By the way, they are negative. I forgot to put negative signs. So not a big problem. Anyhow, we know it is easy to tell that 1, 2, 3, the first 3 coefficients are outside of plus minus 1.96. So these 3, disposable income, price of chicken, price of pork, are statistically significant. But price of beef is too small. The coefficient is too small. So we cannot say it is statistically significant because too small, that means it could be just 0. But we obtain non-zero coefficient by chance as a random error. So that's the result here. Next question. At a concert, a survey was conducted that asked a random sample of 100 people, their age, and how many concerts they have attended last year. A regression model is estimated and Excel output follows. So I would like to explain the number of concerts a person attends using their age. So it is 0.11. 1 more year older, then attends 0.11 more concerts. Then find the coefficient of determination, which is R square of this regression. So it's also pretty standard. You need to read this table. SS is the sum of squares. Among them, we are interested in total sum of squares, 100.79. So this means it's the total variation in your data, variation in number of concerts. And out of them, the regression sum of squares is 91.19. So that is how much you could explain in this regression model. So this is the ratio. This is the percentage, slightly above 50% is how much you explain by this regression model. So that is the coefficient of determination. I'll find that using calculator. Okay, this is it. It's really the end of the semester. I'm really happy. So I really appreciate your work, and you have a nice vacation and happy holiday. Okay. If you need any help, or if you still have questions, feel free to let me know. I'll be happy to help you in my capacity. And if you are interested, particularly if you're interested in more data analysis tools, if you'd like to learn more, then I'm really happy to help you. Okay, so let me know, and thank you.